Okay, folks, let's get started. It's my pleasure to welcome you all to this event hosted by CCI, our Center for Cyber-Physical Systems and the Internet of Things. We've been hosting a number of events. Some of you have attended them in the past that have to do with various seminars, visiting speakers, workshops for faculty, broadly around the theme of emerging technologies and application domains that are starting to be revolutionized by these emerging technologies. And one of the technologies that's very much been in the air, in the news, not just for engineering reasons, but for financial reasons as well, and speculative reasons as well, are blockchain technologies. So we thought we'd have an event where we try to expose our community quite broadly to this technology, really from a tutorial perspective. It's one of those things that's become more and more prominent in the news. A lot of people hear about it. Some of you may have read up on it and know something about it, and others are just wanting to know, what's the engineering behind blockchain. So this event is very much targeted at an engineering audience. We kind of branded it as something for faculty and researchers. We were joking that for faculty, the hardest thing is going back to school. But if you're already at USC, you should be able to have opportunities to keep up with a lot of the recent emerging trends. So we have the event today that's a tutorial organized in two parts. It's in collaboration with Nitin Kale, who's been teaching actually the first blockchain class at USC to ITP students starting this semester, in fact. And he will lead us off with kind of a broad introduction to blockchains, Bitcoin, and Ethereum in particular. And I'll follow up in the second hour with maybe a little bit beyond Bitcoin and Ethereum, looking at some of the other blockchain technologies, distributed ledgers, looking at different business applications, as well as engineering questions that are starting to, let's say, bubble up from the surface in terms of how do we connect all of these technologies to things that we are familiar with from our research interactions in electrical engineering, computer science, and other branches of engineering, and hopefully leave you with some taste for open research problems that are also maybe below the surface given the emergence of this technology and its implications. So we'll get started, and I'll ask Nitin to get us going.
Thank you, Bhaskar. Good morning, everyone. So here's information about the two of us. A lot of familiar faces, for those who are new. I'm Nitin Kale. I teach in the Information Technology Program and Epstein Department ISC. Bhaskar, of course, professor in electrical engineering. So the reason Bhaskar invited me to this because I thought I'd jump into the deep end of the pool this semester to teach a course in blockchain. For our campus-wide audience, we have students, engineers, Marshall students, accountants, economists, so on. So this is a 1 hour summary of a one-semester course. So I have 50 slides, and 50 slides in 50 minutes is not doable. So I will rush through them. We can make these slides available. We'll make the recording available. But this is, the first hour is going to be a tutorial, very introductory. So if you already know, the workings of Bitcoin, then we can come back after an hour for Bhaskar's talk, which is more research oriented. But if you have heard of Bitcoin but you don't know the inner workings, my goal is by the end of an hour, you'll have a deeper understanding. Okay. So it's introduction to blockchain, Bitcoin, and Ethereum. So we'll start with the definition of blockchain, how Bitcoin works as a currency, and then what are some limitations and how we jump from there to Ethereum, then beyond and other applications of blockchain. So please feel free to stop me anytime if something is not clear. So this is kind of my view of some landmark social technological advances in the last 60, 70 years. So from the digital computer, networks, communication, web, mobile, social data, and now the crypto world. Right? Already I think there's talk of crypto economics as a way to incentivize peer-to-peer networks. So today I'm going to focus on this side, like the first 2 or 3 topics here, which is introduce what blockchain is, and then delve into how Bitcoin actually works. Okay. A disclaimer, this I give to my students, and today, so I'll just go to the the bottom line, there is no financial advice in this tutorial. So whether you dabble in Bitcoin or not, please be aware, go to Marshall and take a finance class investing. I am a Bitcoin hobbyist. Investment is a big, I'm not good at it, so I'm just a hobbyist just to see how it works. Of course, today Bitcoin is like $11,000 per coin. So that's a disclaimer. So preliminary. So if you're new to this space, we of course start with some literature survey research, a lot of students here. So if you're already in this space, you probably have read this paper. If not, you should read the Holy Book of Satoshi. This is the paper you should read. It's 9 pages, 1 page is references, so it's 8 pages. Okay? So only 8 pages. I recommend you read it again and again and again. Because 9 years have passed, or 8 years have passed since the beginning of Bitcoin, and we are still uncovering the emergence of things that Nakamoto wrote in this paper. That's a white paper, not peer-reviewed, but it's a seminal paper. So in my own class, I make the students read this at the beginning of the semester, at the midterm, and then the final project. They have to read and answer questions to see if their learning, understanding of blockchain has improved. The word blockchain actually doesn't exist in this paper, at least not directly. It uses the word chain of blocks or something chain, but the word blockchain is not in this paper. So this is available here on the bitcoin.org website. You can get the PDF of this. Okay, so I'm going to motivate a very quick topic on currency. Okay, and then we'll jump from currency to cryptocurrency, Bitcoin, and Ethereum. So, question? Well, what is this? It's a coin, right? So this is a coin from the island of Yap. And these stones are called Rai stones. It is an example of an island that used a very large coin or a heavy coin made of limestone, which was a scarce commodity on that island. So the stone had to be mined or carved from another island in the South Pacific. And the size of the stone was the value of the stone. So this is a house, and a small one would be a goat or something, right? And so to mint these stones, these Rai stones, there are several things they have to do. And I'm going to lead to the topic of a Bitcoin. So first, someone who wanted to buy a house, let's say, would commission workers to sail to this other island and negotiate with the other island's residents that we can come to your island. It's going to 2 weeks to make the stone, carve it out. So we'll trade you and you can give us some food and shelter while our people carve out the stone from the ground. So they carve this out, they're mining it, minting it, and then to sail this back, carry it back, you can imagine this is a small stone, and then commit the ownership of the stone to record this somewhere, ledger. Right? So they have to create a ledger to somehow, as an oral ledger, as a written ledger, and record this somewhere in the island where who owns this stone and where the trade happened between the house and the stone. And you keep this, and over time you never move the stone because it's too heavy and delicate to move it, it might break. If it breaks, it loses its value. So you don't move these, so they just sit in public view. But there's a ledger, an oral ledger or written ledger, that keeps track of who owns which coin at what point. And then you communicate this ownership to everyone. And you trust the person, the ledger keeper. Make sure that this ledger is immutable, somehow doesn't change. This all changed when the Germans came, but that's a different story. But for hundreds of years, this system worked. So you can, if you go to Yap Island, you can still see some uncovered, some that were in the process of being carved out. So this is how you carve it out of the ground. And you can see the distance between the use of this island, of the coins in Yap Island, and Palau is the island where the limestone was. So it's quite a long distance to move this stone by a sailboat or rowboat. So one time, a stone fell over and fell into the ocean. Is this stone part of the ledger? What do you think? Right, it's a question, right? The work has been done. This is a modern picture. At that time, people couldn't prove that the stone was at the bottom, yet it had value. It was called the stone at the bottom of the ocean. And it also has value because the effort was put into it. So people believe it had value because there was witness that the work had been done, and it sank in the ocean, and therefore it was a valid coin. You see where I'm going with this, right? So even if you don't see it, it can have value. So this is a story of dry stone. So here are some important observations about this stone. It is scarce. So it is not found on Yap Island. You have to go and carve it out of another island, which requires some extra work. It is difficult to mine. It's a very large, it's very heavy, it's limestone, several tons. Some of these are, you can see how large this is. You have to expend resources to make this money. So you cannot just make it out of nothing. It's hard to forge. You can imagine that you have to put a lot of effort to make a copy of this, and the copy itself then would be as valuable as the original. It's hard to divide. In fact, if you cut this, it loses a value. You can make it into a smaller stone or make multiple stones out of it. And it's extremely hard to move. So instead of moving the stone every time there's a transaction, you simply change the ledger. You don't move the stone, you say now the stone belongs to person A, or it belongs to Alice, and now it belongs to Bob. So the ledger is what keeps track. The stones don't move once they have been brought to Yap. Okay, that was the motivation, the background of how we did the jump from this to Bitcoin. So blockchain basics. So I have 3 definitions of blockchain. This picture is very important to remember because the blockchain is a set of blocks. The blocks move in the forward direction, but the pointers point towards the back. So today the blockchain is at block N, and block N has a fingerprint of block N minus 1 all the way to block 0. So the blockchain moves forward, the references, the pointers are backward. Here are 3 definitions, depending on what your area of study or your political leanings are. The left is a technical computer science definition. It's a linked list that's built on hash pointers. Okay, so not very exciting. This is what you hear in media, especially coming from accounting and trade and business school. It's a public distributed ledger of peer-to-peer transactions. More, yes, I can understand. And here's the socio-political, economic, semi-technical, libertarian definition. Right? So if you are an iconoclast and you want to say end of business, end of government, everything is going to be peer-to-peer, this is a nicer definition which says open, borderless, decentralized, public, trustless, permissionless, immutable record of transactions. Of course, this is mostly about Bitcoin. So we're going to uncover some of these today. So type of network. So we're going to sit over here somewhere, decentralized and peer-to-peer as far as Bitcoin is concerned. So we're talking about Bitcoin, no central control. All nodes are equal. You can come and join as you wish. There are many protocols in the history that have this peer-to-peer, and Oscar can talk more about this. So we are kind of in this area, decentralized and peer-to-peer, when we talk about blockchain. It's always good to look at where the hype cycle tells us for blockchain. So we are in 2017. So blockchain is over here in the peak of inflated expectations. 2016, when I conceived of a course, it was right at the peak, and you can see your machine learning, deep learning, IoT, it's all over here. Right? So there's blockchain, and ultimately we'll reach somewhere a plateau. So this is from Gartner Consulting. All right, why blockchain? So there's a lot of text on this. I'll just go through some of these. You might have heard these terms. To improve security by distributing the data storage over multiple nodes. So you decentralize, distribute the database. This database is append only. So if you go back here, you can only add to it. So none of these blocks can be modified, and they are secured cryptographically. So if there's any change to any block by a malicious participant, by an actor, then all the participants will know that this has been tampered with. So blockchain is called tamper evident, tamper resistant, even one can say tamper proof. So append only, so you only add transactions, okay, in block n+1. You can store anything that can be digitized. So you can take any asset. Bitcoin, of course, is a fully digital asset, but if you take any asset, ownership of anything, if it can be digitized, then we can store it. It improves efficiency. The transaction fees of transacting between two people can be lowered. There is no central authority, and so there's a big topic called disintermediation. That means two people can transact without going through a bank, an Amazon, an Uber, or any other corporation or institute or any kind of enterprise. People can negotiate, or can transact with each other directly. And the record of this transaction is the blockchain. So one of the things, and I don't have an accounting background, but I'm going to just read up, is one of the things that Bitcoin or the paper solved, Nakamoto doesn't talk about it, is that actually it's a triple entry accounting. And I heard about triple entry accounting just recently. So the Rhinestones are single entry accounting. And single entry accounting is recorded 20,000 years ago until around 1500 in Venice, Italy. Double entry accounting was invented, which people say has actually propelled business and the enterprise itself. So the double entry accounting came first and then the enterprise. So 500-600 years we have used double entry accounting. This is a triple entry accounting system where the receipt or the intermediation is now on the blockchain between two separate entities who have their own books. So they both have their own double entry accounting systems, but the resolution of this is recorded, or settlement is the blockchain. Okay, so more to come about that as I understand triple entry accounting some better. Open transparent, that means at least in the Bitcoin blockchain, all transactions in history are viewable by anyone. Anyone can see the transaction. The identities are pseudonymous. You don't know the real world identity of the transactors, Alice and Bob. They have pseudonymous identities, but you can see every transaction between that has happened from the beginning until today in this immutable blockchain. So this can become an ultimate proof of value ownership. It can bypass governments, corporations, individual criminals, and those are not mutually exclusive. That's a different matter. And it provides extremely strong audit trail. So it has huge implications, not only in business, accounting, in governments, ownership, provenance, and so on. So here's some more definitions. This is not a class, so we'll try to. So we know what a ledger is. It is trustless. That means the system provides a trust. You don't have to trust a person. Alice and Bob will transact and send money or transact or buy a car or a house or whatnot. And the trust is provided by the protocol. The identity is cryptographic. That means you don't have to reveal who you are. You create the identity yourself without permission. So the identity is generated on your laptop. Okay? So if I want to sell Oscar a Bitcoin, I generate and he generates identities on our own computer without going to the central authority to ask for a username and password. We generate it ourselves and only we know it. So this comes with huge responsibility. So if I forget my private key, you're done, that coin is lost. If I send it by mistake instead of to Bhaskar, I send it to Professor Marshak, then I can't. Unless she is benevolent, she'd say, oh, it's mine now. So there is no chargeback, like in credit cards. You cannot say, oops, let's reverse. There's no reverse on append only. It's immutable. This comes with a lot of, we can discuss how to attack and break the Bitcoin network, but it's immutable, which means there has been no known case of a Bitcoin transaction in 8 years, which has been tampered with. There's a huge topic around consensus building. Computer science, of course, teaches consensus algorithms. And Bitcoin uses the proof of work consensus to see who gets to write to this blockchain. So that is a very important. So it's a database, right? So someone has to have right authority, and that person has to be trusted. But in a trustless system, who gets to write? And that where mining comes in. We'll discuss that in a few more slides. It's censorship resistant, that anyone can join. I cannot say I don't like person A, so this person's transaction won't be included, or if they get included, I'll somehow ignore them and motivate the other people in the network to not believe in this transaction. Yes?
So it means that governments can't exclude people either.
Correct.
So that means it's the perfect black market mechanism.
Yes. Yeah, one can say. The FBI, US FBI, has a big stack of Bitcoins themselves also. But the largest known is Nakamoto, I think, has the biggest set of transactions of ownership of Bitcoin. And the second highest, I think, is the Winklevoss brothers of Facebook fame. Yes, they have 1% of all.
How do you know if they have?
They have said that's public.
They could lie.
They could not, yes.
But you wouldn't have to let anyone know,
Yes, yes.
right?
So-
Because you can be anonymous.
Absolutely. And you don't have to have one identity, you can create any number of identities. So if I have many coins, each coin can have a different identity. So I don't have, only I know these identities, but there's nothing in the system that ties all these together into one. So peer-to-peer, no single point of control or failure. Peers can join and leave as they wish. And the network functions even under such higher level of malicious participants. Of course, how to break the network. I think today the value is around the cost to break whatever that means to attack the network is around $3 billion, which is not a lot, which is to gather enough mining power to subvert the system and take majority share in the mining power. It's about $3 billion, which is not a lot considering that Bitcoin is up to a 660 billion market cap. So a government or a bank or institution could quite easily launch such an attack. Decentralized, so nodes on the network hold copies of blockchain. So this is where the distributed peer-to-peer comes in. So in the Rhinestones, there was a central ledger. So the person who owns a ledger has a right permission. And that person you trust, believe it's a CFO of that island, and so on and so forth. In blockchain, what we do is everyone keeps a copy of the blockchain. So I have a Bitcoin running on this. I'm not a miner. I don't have any Bitcoins on this laptop, but I run a full node. Viterbi IT also runs a full node for our classes. There are about 10,000 nodes that are considered full nodes that have the entire copy of the Bitcoin blockchain. So the ledger is replicated 10,000 times around the world. This is just an estimate. And the ledger is about 160 gigabytes. So for now, it's okay, it can fit on this laptop quite easily. So what happens is when a new block of transaction is announced by someone, then that is validated by every node, the 10,000 nodes. They're validated, make sure all the transactions look good. The block is well formed, and if they accept it, they add it to their own blockchain. So now you become n from n to n+1. And this happens every 10 minutes in the Bitcoin network. So every 10 minutes a new block is announced, it is added to the blockchain, and it gets extended. And now after a few transactions, after a few blocks, that becomes an immutable record of a transaction between two people. Yes?
Why 10 minutes?
It was a number that Nakamoto chose in the protocol. It is for efficiency reasons. So if you have very few transactions and if the blocks are very quick, there can be some blocks that might get rejected because two people might propose blocks. And only one block can win. So it's an efficiency so that there's not too many saved blocks. By saved blocks, we mean blocks that don't make it to the blockchain, they are discarded by the network. So it was some number he chose, we don't know how he came upon like 10 minutes. That's an arbitrary. It could be 5 minutes. In other cryptocurrencies, it's 10 seconds. Yes. So every 10 minutes, the blockchain moves forward on average. But if more miners join the hash rate, then the 10 minutes gets short. And what happens is, as more and more competition increases, then these blocks are found faster. So every 2 weeks, the difficulty of finding blocks is adjusted. So it goes back to 10 minutes. Yes. We'll come to mining in just a few minutes. Okay, so nodes all have a full copy of the database, and I don't trust anyone else. I only trust my own blockchain copy. And then as blocks come in containing transactions, I validate each transaction, validate the block. If it looks good, I add it to my blockchain. So now I have the updated history. Any attempt to tamper will become evident to all other nodes, and those nodes will reject any block or transaction that does not follow the rules. Or if there's any transaction in the past that is tampered with, they will find out and they will reject this kind of transaction. So all nodes abide by these consensus rules. These rules were first created as software by Nakamoto in 2009. There's a group of code developers. It's an open source project in Bitcoin. So people can join, update the code, then you do a proposal, and then that proposal can then be added to the set of rules for the consensus.
Could you give an example of a rule?
So a rule that happened recently, okay, I'll give you a very simple rule, which is the most contentious rule 2 years in the making, is the size of this block. So each block in Bitcoin is 1 megabyte. Actually, it was not 1 megabyte. Nakamoto actually slipped that in at a certain time. But anyhow, it's 1 megabyte. And 1 megabyte holds about 2,000 transactions, which is not sufficient for 10 minutes. That is about 3 transactions per second. As more and more people join the Bitcoin frenzy, 3 transactions per second for a global payment system is not sufficient. By comparison, PayPal is like 200 transactions a second. Visa is 30, 40, 50,000 transactions a second, Visa network. Swift, which is the interbanking, is about 400 transactions a second. Bitcoin is 3 transactions. It can be pressed to about 7 transactions. It's not scaling. So the scaling problem of 1 megabyte has become a huge contention. And because it's an open source project, there are different groups of people who want to do different things. Some people say we should double it, linear scaling, so we'll just scale it linearly as and when needed. And then some say we should do some other solution. And so what happened was, sorry, since you asked the question. So on August 1st, there was a group of people, is a split. They said, we don't like this 9 megabyte, we want to make it 8 megabyte or 2 megabyte, whatever it is. And these 2 blocks are now incompatible. So they split and they formed their own blockchain. So what they do is they take the entire history of the ledger, and now you make 2 copies. So one is the old coin, and there's a new coin that will start adding n+1 under different rules with 8 megabyte block. What happens to the old chain? If an 8 megabyte block comes to my old chain, what will it do? It will reject it. Say, I don't know this block, it is invalid. I'm going to only look for 1 megabyte blocks. The 8 megabyte block will say, a 1 megabyte block comes in, that looks good. So these chains have now split. In fact, there are 2 coins now. So one is called Bitcoin, and the other is called Bitcoin Cash. And both groups are fighting for the name Bitcoin. Because, right, I mean, that is really where the investment is. So Bitcoin Cash, people say, we are the real Bitcoin and this is not. Anyhow, so the one that is $11,000 is the old coin, so be careful if you're investing in this. Bitcoin Cash itself is around $1,600, but here's the beauty of this. If you own coins before the splits, you have coins in both. It's called airdrop, you get free money from God, right? So it has split the coin, and now you have money on both coins, in both blockchains. In one, and the market will decide the value. It's not like you have doubled your money, but market will decide the value. And now there's a third coin called Bitcoin Gold that happened just a few weeks ago. It's called Bitcoin Gold. It's worth like $300.
There's nothing to keep this from continuing.
Absolutely. There are 4,000 cryptocurrencies today. 95% have no value, but there are at least 100 which have non-zero value. Many of them are basic copies of Bitcoin. So they take the Bitcoin source code and they change a few rules. They change the proof of work, whatnot, and they create their own coin. Then you tell your friends, oh, invest in my new coin, Kale coin, Master coin, and anything you want. Yes?
So does Bitcoin Gold also duplicate with Bitcoin?
Yes.
So the foundation of Bitcoin was a limited number of coins over
Yes.
time.
Yes.
So is this just counter to the entire philosophy?
Absolutely, yes. So both Bitcoin Gold and Bitcoin Cash have doubled, tripled the money supply of Bitcoin, except that now the identities of the coins are different, and the Bitcoin core, the Bitcoin old Bitcoin, they say these are not Bitcoin. So it is a question of naming rights. Yes. Okay, so blockchain, now you understand what the blockchain is. It provides some proof of state, right? So if you think of it as a global state machine, for financial, it provides that something existed, and there's a timestamp on it. So if Alice and Bob did some transaction, that existence we know. We know the ownership of every coin. From the beginning until today, every coin has an identity, and that identity is recorded in the public blockchain. There's integrity, which is no double spend. There's a long lecture around how Bitcoin solved the problem of double spend, which has plagued for many, many years. How do you stop the double spend in a digital currency? Okay. It provides provenance, the history of owners. So this is a question you asked about black market and money laundering. Even though it does not have a physical identity associated, but if that physical identity is ever revealed, it will show the provenance for all time. So in fact, sort of black market that is now less prominent than it used to be. I'll give you an example that happened recently. A few months ago, there was a malware called WannaCry, right? That would encrypt your files, lock your computer, and say if you want to decrypt your files, send $300 in Bitcoin to this address. The address is a Bitcoin public address. And they published this online. Guess what? Now we know that that public address belongs to WannaCry, so we can track how much money is going there, and if that Bitcoin ever moves and touches an exchange where it is converted to dollars or whatever else.
Can't convert it.
Yes. So that is the provenance which cuts both ways. Right? It cuts both ways. Right? Traceability is trail of movement. Okay. Where is the blockchain? So I don't want to do it now, but actually I should. So if you have never seen this, I think it's worth seeing. So I'm going to just click here. I'm going to just show you the Bitcoin blockchain and how we're doing on time.
Okay.
Okay. All right. Oops, duplicate. Okay, here it is. So if you have never seen, so this is a web wrapper around the Bitcoin blockchain. So this is what the latest blockchain is called, blockchain.info. And you can see that a block, this is a new latest block. This is the number of the block. It came 12 minutes ago. It was created by a node called /pool. It had so many transactions. It moved so much money. And the size of the block is a little bit more than 1 megabyte because this rule was changed recently. Not a lot. It's a little bit more than 1 megabyte, but it is one step towards scalability, better scalability. Let me show you what this block looks like. Okay, so we'll just click on this block number here, and it shows you how many transactions, what time it was created, who related. This is, of course, doesn't have to be revealed. How difficult was it to find this block? We'll talk about difficulty in a few slides. And then it shows every transaction. So here's, forget this transaction for a second, here's a transaction. That means, let's say this is Alice. Alice sent 0.01 Bitcoin that Alice controlled. That means she had the private key for this. And then she sent part of this to this person and part of that to that person. This is the cryptographic identity. This is how you are known on the network. Alice can create as many identities as you want. And this, of course, she knows who these two people are because they have sent her their public address. And now, for all future time, you can track what happens to this coin or any of these coins. So all transactions are here. These transactions can be N to M. That means you can take many coins together and you can split them and send it to many people.
Or in this case, merge it.
Or in this case, looks like they merge it. So they have a lot of small coins in different wallets or whatever. So they combine this. This tells you whether this coin has been moved further. So the word spent is that the coin was used in another transaction. So one thing from an accounting perspective is in this blockchain, there is no concept of accounts. There's only transactions. So there's no balance, there's no running balance. Let me explain that one more time. Okay, this is a very important thing to know. So here is some coin. Alice owns this coin. By owns, that means she owns a private key in order to spend this coin. In order to spend it or to unlock it, she has to know the private key. If she forgets the private key, loses the private key, that coin is lost. It cannot be recovered, at least today. When Alice spends this coin, we destroy this coin. Or we should say we redeem all the value of this coin, and then it is used up and sent to two other people. And therefore, this coin is now spent. This coin is unspent. That means this person has not done anything with the coin, and this coin has been spent. Yes?
So let me get a definition straight.
Yes.
Because you can spend fractional Bitcoins.
Yes.
Does the remaining Bitcoin that you haven't spent
Yes.
get a new name?
Yes.
Okay.
Yes. It doesn't. You can choose how to create that transaction. You could send the change back to where it came from. You should not do that because it de-anonymizes part of your identity. So the analogy that came up with is also happens in US dollar, is when I give you $1 and I want to spend 90 cents, I cannot tear this up. I have to use the entire dollar. And then you give me change and you keep some. That is exactly what happens in Bitcoin.
I thought you just would release 90 cents. No, you sent one Bitcoin and it sends back change?
Yes.
No.
So this is the one Bitcoin. Just imagine this is one Bitcoin. So Alice wanted to send Bob 0.003. The rest of it came back to her as a change. And that gets a new identity if you want. And it is recommended that you use a new identity for that coin. So every time a coin changes, it gets a new identity. This is a very important feature. And the blockchain really reports the unspent part of every transaction. It's called UTXO, unspent transaction output. So in the absence of balances, there is no question of balance because there's no bank. Every time there's a transaction, you destroy the old coin and you create two or how many ever new coins.
So,
Yes.
so this is all kind of coin-centric, right?
Yes.
Following the
Yes.
transaction. But can you also say, well, I'd like to take this entity, this person,
Yes.
and just view all transactions that person has
Yes. Yep.
in and out. So you could
Yes. I
take
think
one step then towards inferring
Yes.
what kind of
right.
accounts might be.
So you can see, I just clicked on that address of Alice. I can see every transaction Alice has done with that address. You
Or
don't
could have
want.
another address.
So
Right.
what you do is to preserve anonymity, you create a new address for every transaction. And the address space is very, very large. It's so it's a very large address space. So if I have to pay a bill, or if I have to buy a house, or if I want to buy coffee, every time I create a new identity.
Oh.
Yes. And that is managed by software called Bitcoin Wallet. So the wallet will manage, you don't have to worry. The software will create these identities and keep all those identities all clean and separate for you. Yes?
But your private key stays the same?
No. Every address, new private key. The private key space is also very, very large. Yes.
Now, does that transaction indicate what the private key is?
No.
So that how is it released, so to speak?
Uh, uh, so private key is a 256-bit number that
Yeah,
only
right.
your computer knows.
Exactly.
From the private key, we use ECDSA, my TA is here. We use ECDSA, Electric Digital Signature Algorithm, to create a public key. And from the public key, we hash it and we create a public address.
I see.
So this is the public address of Alice.
Okay.
And only that is needed to prove that Alice owned the coins,
Mhm.
that Alice signed the transaction to move the coin to Bob,
Mhm.
and that she did not change it after Bob received the transaction. And it provides all this without the private key ever moving the laptop. And that discussion is a very
And that's really crucial.
Crucial.
You never want your private key to leave your.
Yes.
Thanks.
Chuck? I don't
Yeah.
want to take you too deep down this rabbit hole.
Yes.
So if you have your private key and there's some sort of encryption that brings you to every single public address that you would ever post, then if you were to crack that encryption, you could unlock
Yes.
everyone's.
Yes. So all public addresses are in the public domain. It's in the blockchain. But it's a two-step. There's an ECDSA and then there's a SHA-256 and write NP160. You have to break both of those. If you can break it, then you can get all the private keys. The Bitcoin network it'll be gone in like this.
And the more transactions that someone does, theoretically, it should be easier to crack.
No,
No.
short of quantum decryption
Yes.
schemes coming online in
Yeah.
20 years, we're no danger of that.
If you can break one person's, then you can break many people's. If you can break ECDSA, then not only one person will be able to break it for everyone. Okay, so let's put this in a nice picture here. So Alice sends a transaction to Bob. These transactions, maybe 2,000 of them every 10 minutes, they get broadcast to the network using a protocol called Gossip Protocol or flooding. Those transactions are listened by a certain node. They collect them into a block. The node validates the block, makes sure these transactions are good. What do you mean by transactions valid? What we mean is that Alice actually owned the coin, and Alice signed the transaction to move the coin to Bob, and that she did not renege her transaction and then try to double spend it and send it also to Charlie. So all of these are part of the consensus rules where this block and every transaction within is not validated. And if this is good, you tell it to everyone in the network, and everyone now has their own copy of the blockchain. So there's 10,000 of these full blockchains, including on this laptop. So now your database has moved from n to n+1, and so on. And every 10 minutes, it gets added by about 2,000 transactions. Yeah.
Does this indicate then that as you get, this is a nonlinear scaling?
No, it's so far.
Yes,
It's
but
a
if
linear.
if you have 1,000 or 100,000 times as many users.
Yes. So this is a scalability
Yeah,
issue.
that's what I said.
Yes.
This ultimately is
Ultimately, yes.
nonlinear.
So there are already a lot of proposals, and maybe Bhaskar will talk about this, there are proposals so that this does not grow exponentially. Yes. Yeah.
Who makes the block?
So the blocks, the block is a person who has the right authority, right? So this is in Bitcoin is called a miner. So this is a mining, that means the person who does the work of validating gets a reward in
That
Bitcoin.
block become unique, so that
Yes.
those set of transactions only appear in that block.
Exactly.
So that all these blocks are unique.
Absolutely. So if this transaction, if Alice tried to spend the same money to someone else, it will not get added. That's called a double spend attack. It has happened once.
There's some coordination among the miners.
No, there's no coordination. The miners are anonymous.
So what can happen is that two different nodes mine a block at about the same time, and depending on who got added to the chain first, that's the winner. And so if you show up later with a stale block, you're going to be rejected. All the transactions that are in that block, they may not be identical to that first block. Anything that has not been on the block is put back in the pool for somebody else to mine and add to the block. So there's sort of a
It's basically
distributed-
Whoever sends it first.
First, yes.
And actually, it's the longest
Very
chain.
low-level question.
Yes.
What happens to Alice and Bob if that block didn't get validated?
Alice's transaction to Bob will sit in a memory pool with the node or the miner, and they keep sitting until one of the many miners decides to take that transaction, add it to a block. So there is no, in the protocol, there is no expiration date for a transaction. So you just wait.
Either one of them has access to it at that point. So-
Yes. So Bob should not do anything like give her a card until the transaction has been validated.
These things
So
typically
if-
take about an hour or more,
Yes.
sometimes.
Kind of like crypto escrow.
Yes.
Yeah.
So Bob should not give up any asset while this transaction is waiting. Yes.
So the fee is collected by the
Yes.
miners?
Yes. So every time, very good. So actually, okay. I know. So okay, we'll go back here. Okay. So let's go back here. So since Cyrus asked this question about fees, I'll show you what the fee is. So if you go back to this transaction, this is the sending money. This is the receipt. The difference between the sum of inputs minus the sum of outputs is the transaction fee that Alice is offering to any miner to include her transaction, to validate her transaction. That's called the fee. That fee for all 2,000 transactions is collected by the miner who proposed the block, and that block got accepted by the network. So that miner collects all the fee, and the miner gets a block reward. This is where Bitcoin is generated. This is the Rhinestone of Bitcoin, and that has a very special transaction. And that transaction is called the Coinbase transaction, the first transaction of block, where out of nothing, out of nowhere, there is no pointer here, 12.5 Bitcoins are generated as of today for every block, every 10 minutes. 12.5 Bitcoins are rewarded to the miner, plus the transaction fees. So in this case, 0.5 was the transaction fee, and 12.5 was the reward. And this is the address of the miner. So the miner generated the Bitcoin out of nothing and sent it to himself. Everyone got this here? Yes.
So isn't the blockchain is growing
Yes.
as these transactions are happening. So isn't
Yes.
it self-adjusting in terms of the difficulty of work?
Yes. Yeah. We'll come to that. Okay, we are running we're out of time. So I'm going to skip through this. I'm going to skip through this. Also, hashing will just script. If there was a question about how you generate, okay, so too much. So we'll move past this, properties. These are all full lectures in my class. So this is where we come to Bitcoin, all right? So the goal is in us we trust. This is an example of a miner. You can see this is what it requires to mine today. So Bitcoin is actually a confluence of many things that have been advances in technology, cryptography, the blockchain database itself, consensus, game theory, and economics. And all these align beautifully like a cake. If you just mix them together, you get slush. If you follow the instructions and read the paper, then you see how it all comes together to create a bootstrapping currency of Bitcoin. So the word nowadays people are using is cryptoeconomics, and I like this very much. I've spent about 2 years understanding how this actually works. So the reason it's called cryptoeconomics is that cryptography is what secures the history of the ledger. But the future of the ledger is related to economics between game theory and incentivizing and aligning the incentives of miners and investors, etc., to progress the blockchain. Okay? And these are both major topics. This, of course, is run of computer science, and this is game theory, economics, finance, whatnot. So Bitcoin, okay, we talked about this. So you should, the takeaway today is you should remember this name, of course. Satoshi Nakamoto is a pseudonym for he, a person, she, or a group of people. Some people say aliens, or even someone from the future. We don't know who this identity is. I have a linguist, a friend, who has done some research, University of Chicago, to disprove one of the people. Many people have come up. Many people have been alleged to be Nakamoto, including one who lives in LA, Dorian, and there's none. Anyway, there's no, so far we don't know who it is. The private key is used to unlock. Possession is ownership. Possession of the private key is ownership. So if you reveal your private key to someone, they can steal your coins. Okay. There's no concept of accounts, there's only transactions. It's fully digital. There's no physical manifestation. But today, I'm going to give out, for some good questions, a token that looks like a Bitcoin. So for good questions today, we'll give these out. All right. So it has been called many things. Right now, they call it a new asset class investment. But it has many, many different things you can call it. This is a brief history of Bitcoin. So 2009, oh, that's beautiful. So the first block is block 0. It's called Genesis. It has a special place. And you can go from every transaction from then until today is recorded in the public blockchain that I showed you. So there's drugs and WikiLeaks and the $100 million pizzas are here. This is also recorded in the public domain. You can see someone offered on a website said 2 pizzas and I'm going to offer 10,000 Bitcoin for it. So it's $100 million pizza. Anyway, today it stands around here. This was the fork, the split of the blockchain that happened. Anyway, so this is the exchange rate. So these peaks are all related to some news. China does something, or the exchange gets hacked. But now it's just reaching some they call bubble territory. Bhaskar and I were discussing. Like professors have. I should have invested. I should have mined. Professor Shiflett had some ideas. We can make money for USC or something. But there are students at Berkeley and Stanford who are mining in the dorm using the dorm electricity to mine coins 5-6 years ago. Now it's not possible because most of the mining is extremely resource intensive. Okay, so I'm going to talk about mining because we're running out of time. So there's a question of mining. So the node that validates the block and all the transactions within it is a self-professed node, and they are called a miner. So this chart is very important to know. We're going to start with Alice sends Baba transaction, and so this was Professor Heigel's question: is when is this transaction done? So we'll start from there and show when it is actually settled and recorded. So I'm going to show you this story. So this transaction is broadcast to the network. So everyone who's a node will find out this transaction has happened. If the transaction is valid, then the node says, I'll forward it to my peers, to my nodes, and so on and so forth. And within seconds, this will get to the full entire globe. Now, these nodes called miners, they validate all the transactions, but they have to solve a math problem called the proof of work. They have to solve a very difficult math problem, which has no solution but brute force. And it is called hash, or it's to find a nonce, and we'll talk about that in just a second. So they solve a math problem whose difficulty can adjust as the number of competition increases, so that the average time to find the block is 10 minutes. So if people put more resources, then the problem gets more difficult. An example of this is Sudoku. How do I make Sudoku more difficult? Just increase the squares. So the first Sudoku, or Nakamoto Sudoku, was whatever, 9 by 9. Now it is 1 trillion times the size of the first block. It is how difficulty of this has increased, because more and more miners are joining, they're putting more hardware resources to solve the problem, but the problem has no solution but brute force. So the only thing is to keep trying. And the way you try it is you throw more computers, you put a lot of computers that solve this math problem. So when you succeed, when you find a solution, that miner immediately announces that block to everyone.
And the block is found through is the math problem part of finding the block, or is it two independent things?
So they take the whole block.
Yeah,
To the block, they have to add a number called a nonce.
okay,
So the block has a structure, they add something to it,
okay.
and they take this full block and they solve this math problem. That means the entire block plus the nonce has to have a certain hash structure.
Okay. And why is it a math problem as opposed to just a typical,
It's a puzzle.
Fine.
It's a algorithm. It is called SHA-256,
okay.
secure hashing algorithm, and it's a program that they have to take the entire block, add a number 1, find the hash of this, and the hash has a certain structure, then they have 1.
Okay.
If not, they put the number 2 and try again, and 3 and 4 and 5. And they keep trying different numbers till the outcome is what the network has decided as a difficulty.
Okay.
Yes. Okay. Now what happens is, if the miner finds a solution, they give themselves Bitcoin, 12.5, plus all the transaction fees for that block. Whoever does this first wins that race. And now the blockchain has moved from n to n plus 1. The race starts again. New transactions, new 2,000 transactions, new nonce, new math problem, race starts again. The blockchain can only be appended, changes will be evident, and now, Professor Heigl, this transaction is now embedded in the blockchain. So we started from Alice sends to Bob. This takes 10 minutes. The rule of thumb is that even now there is some possibility of an attack. So we usually wait 6 blocks, which is 10 minutes each, so 1 hour, 60 minutes. So after 1 hour, Bob can give the car to Alice, because now it is extremely difficult for Alice to double spend or cheat Bob and take the money back. That's the time. Okay, 3 minutes. So now I have taken this idea of the miner. Cyrus had a question about this miner. So the miner is the one who finds a block and solves the math problem. Okay, I'm going to skip through this a little bit. Divisibility. So the Bitcoin protocol says that the Bitcoin is divisible 10 to the 8. 100 million satoshis is the divisibility. Even that can change through a protocol update. If ever we need more divisibility, so that is 1.6 quadrillion satoshis. So that is enough for the entire world economy. World economy is $100 trillion. So if a satoshi becomes $1 someday, then even then the divisibility is sufficient to cover the world economy. There's a limited supply, so there was a question earlier on. So the supply is 10 every 10 minutes. The miner makes coins, and that is a. So you can see this. So it started with 50 Bitcoin was the reward, excuse me. And then every 210,000 blocks, that reward is halved. So it is a controlled and limited supply currency. So now they became 25, now we are 12.5. So every 4 years, the reward is halved. So it's going to reach a asymptote of 21 million. And the last Bitcoin will be mined in 2140, which will be 1 Satoshi at that point. 1 Satoshi will be mined. After that, miners' incentive is only to collect fees, transaction fees, no reward, no block reward. So right now, we are at about 16, almost 17 million. So 17 million of 21 million have already been mined, so there's an early advantage, so they're very rich early adopters, the twins and Satoshi and who not. Okay, I think we are out of time, so let me...
And can you set your own transaction fee?
Yes. So transaction fee is voluntary. You can also do 0 transaction fee.
So if you want to have others pay attention to the miners, you could offer.
Yes.
Okay.
So this changes. So there are calculators online which will suggest, or your wallet software will tell you what the average is, and so you can choose. Today, if you offer 0 transaction fee, it will not get added. Maybe 3-4 years ago it was possible.
Yeah.
So now you have to offer higher and higher transaction fees. But this is fully dynamic.
Mhm.
Yeah. Yes.
So is the solution of the problem, the math problem, something that has some randomness, or somebody who has a lot more compute can always be the winning winner?
Yes. So the probability of finding the next block is is dependent on your hash rate. So how many SHA-256 computations you can do per second. So if so the probability of finding the next block is your hash rate divided by the network hash rate. Very simple. Yes?
Is the reason you can't mine asynchronously because you don't know what transactions are going to be
Yes.
included?
So there is no pre-mining because the mining uses the entire structure of the blocks, including the Merkle root of all the transactions. So you cannot pre-mine. What you could do is you could create a block with no transactions in it. But even to do that, it has to include the timestamp. So if the clock is moving along, so there is no pre-mining or no asynchronous mining. Yes.
So, I'm sorry, so if the cost of mining is skyrocketing,
Yes.
with the economy of small countries,
Yes.
what's to stop the miners from becoming ticket master and charging excessive
Yes.
transaction costs?
Yeah. So that is where the contention about scaling is coming. So miners, mostly in China, they want higher and higher transaction fees. So they will not include low value transactions. So that's why they say it has to be scaled, so more transactions can come in, so they can still make money and make profit.
So
But the other thing is the value of, right, the US dollar, the value of Bitcoin has been going too.
Right. But the original concept of Bitcoins as microtransactions for the third world is going away.
Yes. At least for now, until there are solutions for sidechains. Okay, so I'm going to skip through this. Wow, I didn't get through all. I had some very, very good examples. But we'll do this again, I guess.
And I have some things that we follow up on. what you
Okay.
said too.
How to acquire? Okay. So you can create a mining rig. Students used to do this in the dorms. Don't try it. It's impractical. You can join a mining pool. Beware. So by the way, remember there's no financial advice today. All of these have pros and cons. The easy one is you can go to an exchange, like you go at an airport and go to an exchange and say, I'll give you dollars, give you euros. You can go and exchange, buy these. You can offer services. You can do coding, students, PhD students, you do some work for someone, they give you Bitcoin. You can use a BTM, there's 2 of them in LA now. So you put US dollars, and then it gives you a private key. You take a picture of that. Okay? Or, this is called local Bitcoins. Please beware. If you see some people hanging out at Starbucks and laptops and something, and they're scanning each other's, that is a cash to Bitcoin transaction. It's called local Bitcoins. That's one way to buy it also. Okay, we're going to talk about Ethereum. I'm going to let Bhaskar take this over. So I'm going to just give you some final thoughts. So I taught a course this semester. I'm very excited. Called ITB 499 Blockchain. I think it went well. I bribed my students. I gave them a very small token amount of Bitcoin. So it went well. I'm going to teach it again in spring. So anyone, students here, faculty, please, you're welcome to attend it. If you want to learn more, okay? So these are some projects to watch. Hyperledger, which is IBM, SAP, many. So this is, you can say, enterprise blockchain. Ethereum is a very good project. I was going to talk about it. If you want to read some books, this is easy to read, more technical, very technical. The second book is one I use from Professor Narayanan at Princeton. He also has a MOOC on Coursera, incredible MOOC. So I use this as my textbook for the class. There are several MOOCs available, and these are people to follow. Andreas Antonopoulos is an evangelist for Bitcoin, and Vitalik Buterin is the inventor of Ethereum, the other blockchain cryptocurrency. They have a lot of videos on YouTube. Okay. I know there's some questions. I'm sorry to ran through all this, but you're welcome. I'll hand out after Bhaskar's presentation. I'm also teaching this class. Maybe we'll do a minor in the future. So, thank you very much, and you are next. Thank you. Do you want a clicker?
No, that's all right. I'll just plug in.
All right, let's take a couple of minutes and I'll switch into second talk.
We don't have anything right on the board.
Maybe not in this room.
Okay.
Let's see what's the.
Do you want to write something?
Yeah, yeah. This is the students.
Do you have a URL?
Just maybe I don't
go find it.
It's very strange.
So, yeah, so you solve the problem, and then you get it right before the next
If any of the students want to get some practice doing smart contracts, I've been authorized by Hyperloop Transportation Technologies to suggest that you go ahead and submit your resume to me or to Hyperloop Transportation Technologies Global, and they're doing blockchain for transport. So if you want any practice to do smart contracts, you can also just send your resume to me directly.
Okay, let's start on the second half of this joint tutorial. So I'm going to go a little bit faster now that you have a baseline understanding of Bitcoin to talk about sort of this whole iceberg below that tip that's starting very slowly to be discovered and to emerge. Page down. Okay. So I thought this is a good way to express the theme of our event today is that, we're just manning this booth in the middle and we're looking for people to show up. So it looks like you all fell for it, but you should have been one of those two other booths. So we heard this whole session about Bitcoin. I'm not going to spend any time on it at all. But this is really the foundation, and that paper by Satoshi that Nitin recommended is definitely the starting point for understanding. So if you start to look at blockchain technologies beyond Bitcoin, your next stop should be Ethereum and learn something about that. What Ethereum added to the whole blockchain space was this notion that those transactions that were recorded could be made a lot smarter. We can allow people to add programmatic transactions, which wait for certain conditions to be met before they're executed. And so Vitalik Buterin and others that worked on Ethereum essentially created a Turing-complete computational distributed computation model on top of blockchain that allows you to then program in various rules and conditions that when they are met, then the transaction completes, certain amount of coins will exchange hands and so on. So around that topic of Ethereum, which I won't go very deep into, there is a whole industry emerging to create distributed applications where completely in a decentralized fashion, without the traditional client-server model used on the internet for web applications, you write what are called dApps, or distributed applications, that are programmed on top of the Ethereum virtual machine using a programming language called Solidity. There are other related programming environments around that, and this allows you to take the idea of blockchain from just being about transacting and sending money to also doing things that are applications that are making use of that transactional layer underneath. Okay, so I do apologize that I don't have time to kind of dig into what Ethereum is, but this is sort of would be your next stop to learn more. There are a number of references to starting with. Ethereum.org would be a good starting point on that front. But if you kind of go beyond Bitcoin and Ethereum, which are referred to as public blockchains, there's another whole world that's emerged, and that is around permissioned blockchains. And so there is this classification between these public blockchains like Bitcoin and Ethereum. Their key feature being anybody can join, users are anonymous, and in order to handle these pseudonymous, anonymous users, you have these very complicated proof of work type of mechanisms, and they have a cost, and the cost we discussed was that they're slow. You get one block mined every 10 minutes on Bitcoin. It's about 10 seconds or so in Ethereum, but there's still sort of limitations on how fast you can accelerate that process. And then I'll talk about some new alternatives to proof of work that are starting to emerge. But fundamentally, this is sort of the limitation, but you get something for it, which is that it's sort of arbitrarily scalable. Anybody can join. You don't need a prior understanding of who the users are before you allow them into the system, allow them to transact, allow them to use the network. It's a very powerful thing, right? But when businesses started to look at what else they could do with blockchain technologies, some of the more conservative businesses, noticeably around Wall Street, but also companies like IBM that saw opportunities in applying blockchain technologies to domains like supply chain, started to think about other ways in which they might want to implement blockchain technologies. And these go by the name of permissioned blockchains or distributed ledger technologies sometimes. And they may be public, but quite often they're either private or a consortium of companies that are participants. And the key difference from public blockchains is that they must have identified users. So you know a priori who everybody is that's on that blockchain entering transactions or participating in it. And if those business use cases allow you to have identified users, you reap the benefit of that, which is that you can do things a lot faster than applying proof of work type of approaches. In particular, it tends to use a whole class of algorithms developed over decades in the computer science distributed systems literature around consensus. And you're able to leverage all of that sort of research base and develop very fast ways of doing transactions, adding new entries onto the distributed ledger and so on. So this is a class of blockchains you might start to hear about called permission blockchain. So examples are Hyperledger Fabric, which is a Linux Foundation effort. There are companies like R3, Ripple, and others. So the phrase sometimes used to refer to these things kind of more broadly than blockchain is distributed ledger technology. So the generalization of what a blockchain does is that it is a database ultimately. It's able to record transactions in chronological order. That database is shared, it's replicated among a set of users, it's synchronized. And in these permissioned distributed ledger technologies, you have some notion of consensus, so that any new transactions that are added are consistently added to all of the copies of that ledger. Still has the notion of digital signatures and hashes, and in many cases it uses the very same notion of adding blocks in a chain, and some new approaches are starting to go beyond chains to trees and directed acyclic graphs and so on, but can generalize past the basic Bitcoin algorithm in a couple of ways. So these businesses that are looking at permission blockchains are looking at a number of attributes of blockchain technologies that go beyond their role and utility as cryptocurrencies. So they're looking for, when you have transactions that show up that span multiple organizations, supply chains are rife with such interactions. How do you all agree on what happened when in a way that nobody is gaming the system, right? There's no falsification. You get this sort of audit trail or provenance tracking capability, and the ledger being append-only, being immutable, gives you certain guarantees. And this notion of smart contracts allows you potentially to encode your contractual obligations as code, so that it's sort of an impartial arbiter of did something happen or did it not, and you move on to the next step. Yeah.
So the consensus is basically the replacement for whoever, the miner who does it first?
Right, so the consensus will completely replace the whole proof of work aspect of adding blocks. So, but there are different implementations of how each of these permissioned technologies might look at it. So IBM has been particularly, let's say, forceful in marketing these applications of blockchain outside of cryptocurrencies. And here are a couple of case studies they have that I'll try to go through briefly. Let me see if I need to plug in for audio. Oops, now something. tested the audio. Okay, so maybe I won't walk through the full video, but just sort of give you a flavor of these two applications. This was a demo that IBM did with Maersk, which is a container shipping company. And they looked at using these distributed ledger technologies to track a shipment of flowers from somewhere in Africa to somewhere in Europe. And along the way, they went through about 19 or 20 different points. There are ports, there are places where it changes hands. And being able to log each of those transactions in a common interface, despite the fact that these different entities may not all have the same interest in mind. So a lot of people ask, why don't you just enter this into a regular database? The difference is just that now each of these entities may or may not have a self-interest in falsifying some of this information. So this is the sort of trust barrier that the distributed ledger technology aims to overcome in that space. So in the slides, you'll be able to see the further details, but that's one piece of it. Let me see what happened to my PDF. Okay. It's not happy about whatever I'm doing. Okay. And this is another application which is with Walmart, where the supply chain question is really tracking down the provenance of individual goods in the store, particularly food items. And so if you have, the example they use is this box of mangoes in the store, and you want to know everything about tracing back where did this mango come from, what hands did it pass through. If you have any food safety issues, you want to issue recalls, or you want to trace back what is the particular shipment that was affected. Again, it's not coming directly from a farmer to the store, it's going through many hops in the way, and to be able to kind of trace back through each of those steps is something that Walmart, for example, cares about. So they're adopting the IBM platform, which is based on Hyperledger Fabric for their applications. So again, the use case has to do with crossing trust boundaries, recording exactly what happened when. Yeah.
Is this based on sensors that are
I believe that current demos are fairly manual, but this is also where the intersection of the IoT shows up, is during the supply process, if there was a truck that was carrying the goods, if you have sensors on board that are measuring temperature, you could also log those temperature readings to the extent that you trust them to be calibrated and correct, to also give you that profile. And so you can go back and say, the shipment was damaged, the record shows that the temperature was above the nominal level, and you can have sort of assigned liability issues, assigned liability based on that.
So with Bitcoin, if I get Bitcoin from several people and then I transfer some to you, once I get them, they're all one kind of thing. They're all Bitcoin. I transfer it to you. There's no keeping track of, which ones I got.
Which particular ones
right,
yeah.
went to you. But if you're looking at supply chain, right, there are different components to
right.
the machinery, or there are pesticides that are used.
Sure.
Okay. I presume that they're talking about modifying the concept of blockchain to keep track of those
what you
different
care about.
components.
Right. So it is a significant generalization from Bitcoin, not focusing on just the transactions of coins, but these database entries, which might talk about very different types of information that's being tracked in there. So it is generalizing past that considerably. Typically, in the Hyperledger Fabric environment, in these examples that IBM's worked on, you have no more than 15 to 20 participants in the entire blockchain. So that's the other difference. Transaction speeds are much, much higher, thousands of transactions per second, but the number of nodes in the entire network are a couple of dozen. Right? So there's a kind of different space that it occupies as far as the...
And is IBM doing the validation?
No. The whole point is when you're deploying this, there is no centralized company that is going to be in charge of validating. It is still a completely distributed, decentralized protocol. That is ultimately the benefit.
Are there still miners?
There's no notion of miners. This is replaced by a notion of having a consensus algorithm in place that kind of fairly allocates how the blocks get allocated. So Hyperledger is a Linux Foundation project, has a large number of members. One of their projects is called Hyperledger Fabric, which is an open source permission distributed ledger for these types of supply chain applications. The way it works also is that members only see the transactions that they participate in, so not everything is sent to everyone, which in the business environment might have certain confidentiality issues that you also need to address. So it does differ quite a bit from the Bitcoin example before, but somehow the core notion of decentralizing this validation of events happening over time, using actually still the same notion of blockchain to give you this feature of immutability. Those features they have in common, but there are also significant differences. In particular, the Hyperledger Fabric open source software brings into the picture a lot of consensus algorithms which always assume that you knew the identity of the participants. So all of this literature in computer science around consensus, those algorithms require that you know the ID of the participants. If that condition holds, you can leverage all of that framework. The default consensus algorithm used in Hyperledger Fabric is something called practical Byzantine fault-tolerant consensus. But these are sort of plug-and-play components. You can take other consensus algorithms that are in the literature that you develop and use them in conjunction with this capability. Here's another example of a permission blockchain for the financial system that's called Ripple. They're very much focused on transactions in a finance setting, and again, trying to aim at much higher transactions per time, and using another Byzantine fault-tolerant consensus algorithm of their own in this case. In this case, they also have associated with it their own currency called XRP. So if you hear about other currencies in permission blockchains, here's one example of that. So what's growing around blockchains is people start to think of it not just as cryptocurrency, but as a set of building blocks you can use to cross certain barriers that might have existed before. The biggest one is trust. Then it sort of opens up possibilities in the application space. I like this particular slide that kind of breaks down the applications that are emerging broadly into 4 categories. Digital currencies are what most of us are familiar with, transactions, payments, and so on. Record keeping is kind of the class of applications we just discussed, these distributed ledger technologies. Smart contracts are the kinds of things that Ethereum is starting to enable. And in addition to these, in the finance industry, there's also a lot of interest in putting securities on blockchain, securitizing sort of real-world assets and having ways to share them, trade them, and so on. Here is another application domain, maybe closer to engineering, which is smart grid. So there are a number of projects that have kicked off this year around the world, in the US and Europe in particular, that are looking at the blockchain piece enabling transactions or trading of energy. So if you're generating energy, if you want to sell it to your neighbors in a microgrid, this is the Brooklyn microgrid experiment out of New York, or you're buying and selling back to energy companies. There's a company in Austria called Grid Singularity, which is using blockchains for energy trading. Or for electric car fleets, as they're charging, how do they transact charging fees in a way that's completely effortless and invisible to the driver in some sense, without taking up a lot of your mind space as you're navigating and parking and charging and so on. So there's a number of activities around that. There was a great issue of IEEE Spectrum that just came out, I think 2 months ago, or is it October or September, I forget. In there was, and on the website for Spectrum is this great interactive feature of, do you really need a blockchain to solve your problem? There are many startups and what are called initial coin offerings, which are using blockchains to solve problems that they didn't really need blockchains to solve. But it has to do with essentially questions around, do you really need this notion of trust that blockchain is really addressing? Do you have anonymous users? Do you have permissioned users? And depending on that, the answer might be don't use blockchain, or use a permissioned blockchain, or use a public blockchain, right? And so there is some kind of a decision process one can make to understand which fits best for their applications. So I mentioned that these algorithms and distributed consensus have proven quite central in the space of permissioned blockchains. I'm going to do this rapid, maybe 5-minute version of kind of a review of that literature. So consensus in computer science is broadly these three things. All nodes, you want them to agree on a value that was proposed by one of them. And it must happen. Like at the end of this consensus algorithm, they must all agree on that value. So there is a lot of theoretical literature on this subject. In particular, a famous result says that you can't actually guarantee in a totally asynchronous network where messages can be delayed that can terminate in every execution if you have the possibility of certain types of failures. Okay. And so achieving consensus is a hard problem, particularly if you want 100% guarantees. Nevertheless, there are things you can do in a more practical setting. And there's a whole literature around consensus algorithms that are efficient but are not necessarily crash resistant. The simplest type of consensus is called two-phase commit. There were solutions proposed in the 70s and the 80s to improve the failure resistance of consensus algorithms. Paxos by Lamport is a very famous example of that. In fact, it was a brilliant proposal that was so brilliant that nobody understood it for a decade, and then people started to use it, and he had to rewrite his paper, and so the paper called Paxos Made Simple is the one that people finally understood. There's another consensus algorithm called Raft, which I encourage you to check out. It's very understandable, very easy to get the idea. Essentially, there's a phase of leader election, and then the leader in each phase gets to essentially collect all the information, make a proposal, and everybody else accepts it, and then you keep swapping leaders through that distributed leader election process. In that literature, there's been a lot of focus on not just crash resistance, but also resistance to malicious messaging that might happen in the network. Nodes that are sending wrong information or misleading information, can you still achieve consensus despite such agents being part of your system? And so there's a class of algorithms that have been proposed over the years, in the last 10 years or so in particular, 10, 20 years or so, that are meant to handle what are called Byzantine failures. And a lot of the permissioned blockchains that I mentioned, Ripple, R3, Hyperledger Fabric, are using these Byzantine fault-tolerant algorithms in their design. There's also, this is a chart that kind of compares different algorithms with respect to various properties people care about. So when you talk about Byzantine fault tolerance, you also talk about sort of what fraction of nodes can be malicious and I can still handle it. Something like a third of them being malicious is generally okay. Algorithms can handle things of that order. What's interesting is that if you think of proof of work, the algorithm that's in the original Satoshi paper, it was a daring, lateral, out-of-the-box way of thinking about consensus that broke many assumptions that the academic literature made about consensus. First, it said we don't even need to have identified users. I mean, that was big, right? Second, it said because of this way that the price of work mechanism is employed, that you're able to handle up to 49% of the network behaving in malicious ways. So it sort of gives you some advantages there. There are things it does lose. The biggest thing it loses is throughput. It's not as fast. It's not able to execute as many transactions. It requires a lot of CPU usage, and I'll get back to that in a bit. And it gives sort of a probabilistic consensus guarantee that the further back in the chain you go, the probability that valid transactions could be changed and so on becomes exponentially small. So it changes certain assumptions, but you could think of it and place it and compare it against all of that literature by saying that it was sort of not following the same set of assumptions, but giving you a different point in a larger, much larger design space than was previously believed to be relevant or interesting. There are also ties to the database literature. There are notions of consistency in databases. Again, I won't get into it, but for people that are interested or already familiar with it, there's a CAP theorem that looks at kind of in a distributed database system, what are certain properties you can guarantee. And there are database systems, traditionally SQL-based data systems, that can give you certain guarantees. More recently, a lot of NoSQL databases weaken some of those guarantees, but improve availability, for example, and scale, but are less consistent. There's still an ongoing debate, if you will, in the literature about what types of guarantees with respect to these ACID and base guarantees that people know in databases are provided by blockchain systems. The definitive blog post about it seems to be by Emin Sirer from Cornell. There's a paper that just came out, I think it's probably still a preprint, that tries to argue that there's in fact a completely different consistency model that blockchain technologies are providing that is neither ACID nor base, but sort of its own category, and these are the properties of this new category of distributed databases. So if you come at this from a database perspective, there's some richness of questions to explore. Again, because if you have this very rich design space that people since the 70s have been looking at, and you get something that comes out of left field and changes the assumptions and gives you a working large-scale prototype, you have to start thinking what else is missing, right? So then that's the research opportunity for engineering researchers. So very quickly, Bitcoin itself, built on top of prior proposals. Hashcash in particular was proposed in '97 as a solution to reduce spam mail. So this idea of solving puzzles. So the idea was that every time you send an email, you have to spend some effort, solve a puzzle, and prove that you solved the puzzle before you can send me an email. And that this would be a way to deter spam. So back in '97, this scheme called Hashcash was developed. The proof of work in Bitcoin actually uses essentially the same thing. Here's the entry on Hashcash. The difference essentially has to do with which hash is used and what the conditions are that need to be met for the puzzle to be solved. But it's essentially what is the building block in Bitcoin.
So when you say proof of work, you're really talking about solving the mathematical.
You literally want them to spend some time doing something because just to give you an intuition, what does this buy you? If I have the ability to pretend to be anybody at all, right? What prevents me from generating 1 billion public addresses, all of which are quote unquote mining and generating a block? I have to create some barrier that people have to spend real effort in order to generate that block, right? So that's the barrier that's imposed by proof of work. And as a result, I don't need to identify every single user. Even though they're anonymous, I put limits on what they can do, right? So that's intuitively what proof of work is giving us. Anyway, so there's sort of clear connections to that prior work. However, this proof of work suffers from issues. The biggest is it's led to a computational arms race. What it takes now to mine Bitcoin is, at a minimum, you have to spend about $10,000 to $100,000 to get state-of-the-art mining equipment that in a year's time might be obsolete. This statistic really is mind-boggling that we're spending more electricity a year than an entire country just to mine Bitcoins today. Moreover, there is this notion of a 51% attack, and it seems unlikely that you'd get 51% of a network colluding, but it's 51% of the compute power. And the numbers are a little outdated now, but the calculation I saw was that it took about $1 billion for a nation state to buy enough compute power to get to about 51%. So maybe now it's 10 billion because the prices have gone up. But the point is, it was not out of the realm of possibility for North Korea to start, throwing around some weight on the Bitcoin network. And of course, slow. So people have looked at alternatives to proof of work. So the main notion is we want to do something that will allow us to somehow pin down not identities of these anonymous users, but make them do something to participate. So raise the barrier to participation in some way, right? And so there are a number of alternatives proposed. One that's been adopted actually in a number of public blockchains, including Peercoin, NXT, and so on, is this notion of stake. So your probability of mining the block is proportional to what fraction of the coins you own. So if you put up those coins as a stake, you get a higher chance of being able to mine a block. Ethereum, for example, is one of these very popular blockchains that's slated to switch to proof of stake at some point. Another alternative advocated by a blockchain called NEM, or a group behind a blockchain called NEM, is to have some other notion of an importance score that has to do with how central a node is in the graph of transactions. Those of you familiar with some of these network centrality types of notions. So employ that to give higher score to certain nodes than others, and they get a sort of higher probability of being able to mine. And again, somehow it all has to do with also aligning the incentives in such a way that if you have a higher stake, it's in your favor to keep things going well, right? And so that's sort of a part of the design here. There are other schemes that have to do with proof of space, where miners allocate unused disk space to the network, and how much you contribute in terms of space to the network is what you can have. There's a blockchain-based distributed storage system called Storj, where that's the basis for mining, and the whole application they have is for distributed storage anyway. So you free up storage for other people to use. They can transact and buy and sell storage from you, but the more storage you're willing to put up, the higher the chances you can also reap these rewards from it.
Yeah, in the discussion of all three of those, do they have ceilings put on them? Because all three of each monopolies.
The first one, very clearly. The second one, possibly so. I'm not actually sure if there's a ceiling function explicitly in the importance score function either. Proof of space, again, if you're willing to buy up all the storage space and provide it to the network, you get a higher share. But part of this, again, is aligning the incentives. They want more space available for people to use on their network, so they're kind of incentivizing what they want in terms of behavior. So my point here is that these are probably not the end of all the proof of X things we're going to see. These are examples of creative thinking beyond the proof of work. And most of these don't require CPU usage of that scale. There are other problems with Bitcoin. We talked about scalability. There are various efforts to directly improve the performance of Bitcoin. We heard about Bitcoin Cash and Bitcoin Gold. There's a tricky thing where if it's a soft fork, meaning it's backwards compatible, things are relatively easy. But when you propose a change that requires you to completely break it up into separate chains, things are a little bit more risky or challenging. And so we're seeing some of those being worked out in the market. There's a lot of news about various ways in which cryptocurrencies are being stolen and lost. A majority of them can be traced back to sort of transient learning curve of, for example, deploying smart contract as code where the code has bugs in it. And we just, are in such early days of developing these systems that programmers are still figuring out what are best practices. The tools don't really exist to verify the software for even known bugs, let alone new bugs that might be introduced and so on. So from a research perspective, I think securing blockchain technologies, bringing the array of techniques we have for software verification and testing to blockchain software, I think there's a huge space there that's still starting to grow. Won't get into any specific examples there, but okay. So then I want to kind of conclude with a set of pointers to the intersection between blockchains and distributed network storage and computation. So sort of this phrase I find very appealing is thinking of Bitcoin or blockchains as providing a trust layer for the internet that it was missing. And a concrete example of a scheme, a paper that has started to address this issue is, or sort of a whole blockchain, is called Blockstack, where they're looking at application layer distributed protocols on the internet that even though they should be distributed, were actually centralized and were bootstrapping trust from our trust in known authorities. And DNS is a very classic example. This is the protocol on the internet that we use to figure out what is the IP address for a given URL, right? And so ultimately, this is governed by ICANN. There are root servers that we trust. There's one at ISI, at USC, so we are truly trustworthy. But in the interest of progress, we have to move to systems where you don't need to have earned that trust out of band, but it sort of comes as part of the natural way in which blockchains operate. And so Blockstack is this notion of creating a completely decentralized registry. There are no root servers, there are no trusted entries a priori, but you can essentially create the same capability, and they demonstrated it, of whatever DNS offers. So there's something called the, what's it called, BNS? There's a blockchain name service, and Blockstack has a whole implementation to go with it. And so there are certain benefits you get from putting it on a blockchain. You are relieved from central points of failure. Somebody hacking into one DNS server can't poison the cache for other users. And also you can have sort of these names being kind of stolen from other users and so on, because you have this cryptographic binding with the private key of the owner. So yeah, Blockstack would be a good example of such an emerging system to look at. Public key infrastructure is another example of an application layer protocol where we are really trusting root certification authorities and our trust in them, VeriSign and others, to bootstrap trust in all the websites we visit when we type in HTTPS something, right? And so again, it is possible to conceive of an implementation of the public key infrastructure where you get rid of the need to trust one central authority and kind of distribute that trust in such a way that you really just bootstrap it through a blockchain. And there is something called CertCoin, which is a system that was proposed a few years ago that demonstrates how you might be able to do that. We talked about the permission ledgers. There's also an effort called BigchainDB, which is also looking at creating a database layer for blockchain applications. This kind of is their picture to show what they're hoping to achieve. So just as cloud applications run on cloud platforms, use some cloud computing resource, any kind of database on the cloud, a file system on the cloud, you have this sort of parallel universe of decentralized applications that run over a distributed blockchain-based computational environments such as Ethereum's virtual machines, use their database system and a file system that's also blockchain-based, and there's an example of that called IPFS, which I think was my next slide right here, which is a peer-to-peer distributed file system that's also kind of connected to blockchains, where they are essentially trying to get away again from decentralized authorities, creating incentives for people to provide storage, for people to make it very easy to query content and find it over in this case, a distributed hash table, links for which are placed into a blockchain transaction that you can look up and follow. So you get timestamps for your content, you get security for your content. You don't put the whole data on the chain, you put pointers to the data on the chain, and then kind of use it in that way. There is an effort out of some folks in Europe, Indria and others, that have done research on decentralized cloud computing, creating kind of a side chain where you have users providing their computers. If you remember the old SETI program had a grid computing implementation. You could run search for extraterrestrial intelligence on your computer. Well, now you can do the same thing but get paid for it. So essentially, that notion, IXEC is an example of that. In the Internet of Things, certainly something of personal interest to me, there are barriers to adopting blockchain technologies directly, having to do with the scalability, the speed of transactions, even the transaction fees. If we're really talking about small bits of data, maybe I only want to pay, millicents per datum. What would that transaction look like when you're going to charge me transaction fees on top of it? So can we reduce the transaction fees is a question. Hardware requirements. Can I run the system with Raspberry Pi or low-power embedded processors as opposed to computationally intensive miners? Can you handle network partitions where nodes may not be connected at all times? And so there is a blockchain technology called IOTA, and Tangle is their name for a directed acyclic graph implementation of blockchains, which allows for temporary partitions and reconnections while still maintaining some of the properties that you need for blockchain transactions to go through. They claim they can, in a public blockchain, get up to 500 transactions per second, which starts to match things you see out there. Oops. Yeah. So this is another example of problems being looked at, addressed, and at least some current work on it. The world of blockchains outside of Bitcoin and Ethereum and Hyperledger Fabric and Ripple and IOTA, which are maybe the top 5 things I hear about, is vast. I mean, there are hundreds and hundreds of things people have come up with, some of which are more interesting than others. I just list a few I found interesting. I have not necessarily studied them in some detail, but stop. Okay. Cardano is a blockchain that's just emerged. Seems to be very academically driven. There's a lot of research papers behind it, a lot of thinking about layering, a lot of thinking about lessons learned from the past experiences, not just with blockchain, but other distributed computing systems, how to do governance in a way that's sustainable in the long run. Not sure what the problem is actually here. R3 Corda and Symbiont are permissioned distributed ledger technologies that in the finance space are quite prominent. Hashgraph is a permissioned DLT, also based on directed acyclic graph instead of chains, that claims to be very fast. Steemit is like Reddit, except now when you post something and people upvote it, you get money for it. So the claim is that you'll get more quality content when people have an incentive to post quality reports or articles and notes. Simple Token was something that came out recently that tries to make it easy to create tokens for miniature economies. So if you want to create a local economy around your own named token for a loyalty program, for whatever use you want, you can just use Simple Token to kind of build without having to worry about all the complexities of the underlying blockchain. So creating sort of abstractions to program over blockchains. Lisk is another example of such an abstraction, in this case based on a JavaScript API library to facilitate such distributed app programming. And Cypherium is something else that's new. Basecoin claims to be trying to build a cryptocurrency that's not subject to all the volatility and fluctuations that you see in Bitcoin and so on. I can't say I know a whole lot about it, but the point again is that there's a lot of activity happening out there from many perspectives. So I think for researchers in engineering, there are a number of open directions to pursue, from mathematical modeling to thinking about ways to improve scalability and performance in quantitative ways. The state of the art in blockchain technology today is you write a non-peer-reviewed white paper, you start up a company, you create a buzz, you create an ICO, you get people to talk about your stuff in forums, earn a few $100 million before you even have a few tens of lines of code, and then exit. I think in the next 10 years or so, we're going to slowly see more academic thinking, more rigor applied to blockchains, better understanding of quantifying what is the problem, what is missing, how to solve it. So I think this really is the time to be thinking more deeply and slightly longer term. New architectures are still wide open. We've talked about blockchains and directed acyclic graph-based architectures, but there's maybe other things to do to think about their connections through some of the concepts I described before, to distributed networking, storage, computing, IoT, smarter contracts with machine learning if you're a machine learning inclined person. So I think a lot of traditional areas in engineering are seeing a direct connection to these emerging technologies. So if you work in any of those spaces, I would encourage you to take a look and see where you can dig in deeper. All of the slides that I have presented and that Nitin presented will make it available online. I have a reading list that I put together this semester that's available. The folks behind Cardano have created an online research library for blockchain technologies that has a good collection of research papers on the subject. We are trying to pull together all the activities happening across USC at blockchain.usc.edu, so please visit if you haven't. We're trying to organize a symposium next spring. If you have ideas for papers in particular, we'd love to get submissions. There's a link to that. And Nitin has done a wonderful job of jumping in and getting us going to lead with the ITP course. And in spring 2018, I'm also teaching a special topics research seminar in computer science as well. So those are some resources to follow up on. So we're happy to conclude our tutorial and take questions. Thank you. Nitin still has
I'm going to give these away. You can
incentives.
ask, we'll do this. You have to earn it, like a miner, you have to earn these.
I thought they have to ask the questions, right?
So when someone says blockchain collisions, are they talking about two miners trying to submit the same information?
So no, so there's two different things. So collision is a hash collision, which is a property I was going to go over. So it's for so if you give it two different inputs that they hash the same hash output. That's called a hash collision. It is not feasible to find it because the space is so large. If a hash collision is found, that will undermine at least SHA-256, which is the hash used in Bitcoin. Not all cryptocurrencies use the same hash function. So that is a collision because, and so the corollary for that is if so if two things hash the same thing, then they must be the same. That is a underline.
Two transactions.
Two inputs. They could be transactions, it could be identities.
Question, Becca?
Yeah, at the beginning you said the miners, they can set up the resources in the dorm, etc. But now it's become the more complex problem. It means again, it's like the retail is controlled by Amazon. It's become controlled by the big companies, right? More and more.
Yeah.
The more resources, more countries puts the resources behind that.
Yes. So mining, so I think the way to say that is mining has gotten more centralized. So it was possible for students to mine Bitcoin in the early days, 5-6 years ago, in the dorm using even a laptop. Then they started creating these rigs. I showed you a picture. And now mining farms. They have mining farm. There's the biggest mining farm is called Bitmain. It's in China, which has I think 5,000 miners. So these are computers that do only one thing, which is to do the hash SHA-256. And now there are giga hashes per second. So there's 5,000. Each one is $2,000 or $3,000. That is just the cost of the equipment, plus electricity to run it, and the electricity to cool it. To cool the space.
So they're often placed in places where electricity is cheap.
Yeah.
I think it's something like 3 cents per kilowatt hour.
So cheap electricity, or in Iceland, I think there's a big mining farm coming out in Russia. I have a student this semester in my class whose family owns a mining rig in Mongolia. Where the power is cheap, is coal farming is coal. So about 3 cents.
3 cents, that's
per
what
kilowatt.
So about Bitcoins being lost or stolen, right? So you had a chart there with all the hats. So I can understand how it's lost, right? My computer gets destroyed,
You
there
lost
goes
the
my
private
private
keys.
key,
Yeah.
the money's gone. I don't quite understand how it's stolen, right? Someone can gain access to my private key, but they have to move it somewhere, right? And then they don't have to move it. We know.
They can move it. They can move it. In the moment, in the game, the first thing they'll do is move it.
But we know, right?
Which
because-
public address it went to?
Right. We know where it went to.
Yes.
We can blacklist it,
Yes.
whatever people do with this, right? So what use is it if you steal Bitcoin?
Right. First of all, I don't think there is a blacklisting choice. So if once it's moved, and typically they'll just split it into 50,000 different public addresses, right?
Well,
Each
we
of which
know
will
what
have
they
small
are.
amounts.
Hey, databases can keep track of all.
You
of
absolutely
this.
know all of them, but there's
And
no
I would be surprised
blacklisting.
If there's someone who maintains a database
Right.
of bad.
Well, let's say they just use it, in a valid transaction and hand it over to Starbucks. What are you going to do now?
Well, I mean,
You have their public address, but it's
reputable
utterly
places
useless,
to
and they're not going to
commit
use it ever
to
again.
not accepting.
Yeah, and they will never use it again, right? So getting at it right away, blacklisting something like that might work, but it's not in the architecture of Bitcoin to be able to do that.
There's blacklisting has not happened. There's a blacklisting attack.
Blockchain system for blacklisting, right? I mean, you can do
Blacklisting
it the
service.
same
Yes,
way,
yes,
right?
yeah.
Where there's a
Yes.
distributed database of these things. So it sounds to me a little bit like stealing Bitcoin or hacking to get it doesn't have a good future, right? Unless there's a separate economy of,
Yes.
bad guys who will. don't
So
care.
there is, but that's also a question of fungibility, right? So I think the protocol doesn't guarantee, but goal aims towards fungibility. So every coin is the same as any other coin. But there is a way to blacklist. Miners can blacklist, but it is a function of hash rate. So there is a kind of a blacklisting is called feather forking, which is an attack which says you publicly tell that I'm going to blacklist this transaction, this coin is bad, and then the miners, other miners will believe you, and because it incentivizes them to not create a block in which that transaction is included. Yeah, so there's a blacklisting, absolutely. I don't know if blacklisting has happened successfully so far. I'll give you just one example. We are out of time, but I'll give you a very good example. This has come out as not a blacklist. So Satoshi Nakamoto, there have been some papers written about how much Nakamoto himself or herself mined and owns. Because we know for a fact that the very first coins, and this block number 1 and block number 2, those coins have not moved. And people are watching those coins. So they were mined in 2009, and because he did use different public addresses for each coin, it's hard to say, to map them all to him. But definitely for the first several months, they were his coins because there were very, very few other people. So there's a claim between 1 and 1.5 million of the 17 million so far mined are owned, controlled by Nakamoto. Nakamoto has not moved them, presumably. So there's been, someone says that if 1 million of them get dumped into the economy today, it will devalue. So they have said that we should blacklist them and do a hard fork, thereby eliminating those 1 million from the 17 million economy. That hasn't gone well there.
Early on, you said that your laptop was a node and
Yes.
gave us the code for
Mhm.
us becoming nodes.
Yes.
As the number of nodes increases, doesn't that put a limit on the speed at which the ledger can be updated? Because doesn't it have to check all potential nodes to see they're online?
So the nodes are these, so I'm not a miner. There's a difference between a full node and a mining node. So miner simply takes a copy of the blockchain and keeps it for themselves. And this way I don't have to trust anyone to know a transaction, I only trust myself. The miners are the ones who get the right capability, who can extend the blockchain by 1 block. So those miners, we don't know how many there are. There are pools of miners, it's very hard to know how many miners there are. And it's very hard to know how many full nodes there are because they could be hiding.
So when your laptop goes back online, it just looks for the latest
Block
update of the ledger.
updates of that of the
It does a
blockchain.
sync, so I can show you later. So I have turned off I haven't run the software for 10 days. So let's say I'm at block number 10,000. So then it says who amongst the peers has 10,001. I grab it, I don't copy it, I validate every transaction and validate, then 10,001. So that catch up will take a few hours.
Sometimes a few hours.
Yeah, it takes a few hours, then catch up to today's latest block. Now I have a full copy of the entire blockchain. So if I'm a merchant, if I'm Amazon and Access Bitcoin, I should have a full copy of the blockchain so that I know the entire history of every unspent Bitcoin. Yes.
So you mentioned there was like an intermediate state for a transaction where I spend the money, but until it gets in the block,
Yes.
I don't get anything back from it. So like, is it possible to like cancel a transaction if it stays there for too long?
So transactions don't have an expiration date. So they go out in the network. The miners keep all the transactions outside, and they will prioritize them by fees. And they'll say, I take the top 2,000, include them in a block. Right? Once they include in the block, the other miners cannot include because that could be considered double spend. So in this period, the transaction is known to everyone. I can look it up online that Alice has sent Bob some money, but it is not invalidated and added to the blockchain. So that is the intermediate state. You don't trust the transaction.
But was your question that then can you cancel it?
Oh, the
Yeah,
yeah.
No.
No, so there is no cancellation. There was a blockchain update, let's say you put 0 fees, and it sits and doesn't get into a block, well then what happens? So miners have some own strategy. This is not part of the protocol. They can dump the low value transactions after a few days because it clogs up their memory pool. So they can just dump the bottom ones. But all miners have to do it, otherwise one of the miners might include it. So there was an update called replace by fee. So if you offered a transaction with very low fee, you can put the same transaction again with a higher fee. And the miner will then choose a higher fee transaction.
But that's still not letting you take back a transaction.
Yeah, so there is no cancel. Once you hit send, there is no cancel, there is no undo. There is no
So how is that shared with everyone? So you haven't created the block yet, but how does everyone know that?
Oh, because the transactions were already broadcast to everybody.
Yes.
Okay, so
There was a flood of the transactions to every node.
so there's a race to
Create the block, but everybody has all the, yeah.
Yes.
Does that mean that I can then do a double spend? If that's waiting for no transaction fee, and I do spend that same Bitcoin with a
Yes.
higher transaction fee,
Yes.
then the race of the block, I beat the race of the block because someone's going to take the higher transaction.
Yes. So now you have two transactions, one with 0 fee and one with a higher fee. Whichever transaction makes it into a block will become the valid transaction, the other one will become a double spend, it will be rejected by the network.
So I could say, Kwame, I'm going to send you some money, but I put 0. And
Yeah.
then say, Phil, I'm going to send you some money, that same Bitcoin,
Yes.
a higher transaction fee.
Only one will make it.
Only one will make it.
And once it makes it, the other one automatically becomes invalid.
So that's the only way in which a transaction
Can-
is ended, is that it's declared invalid.
Yes.
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 But
Yes.
that means if you're doing a transaction and you're time dependent, what do?
So if you
Yeah,
provide
on the-
if you provide sufficient transaction fee, it takes 10 minutes, which is a lot faster than a bank which takes 3 days to do a settlement. By the way, this is a settlement.
Right, and
The
yes and no in the sense that most receivers will wait about 6 transactions before they'll confirm it. So it's typically more like an hour. So if you want to do something within a few seconds, you're out of luck. Bitcoin can't do it within a few seconds.
All right.
So the transaction is visible within a second everywhere. The confirmation or the settlement of the transaction takes
That
10
takes,
minutes.
right,
And if you want to be absolutely sure that this transaction never get reversed,
reverse.
you
You wait about
6
6.
blocks or 6 confirmations, which takes about an hour, and then it's considered
I
immutable.
mean, if you're receiving Bitcoins, you're advised to wait that length of time because then sort of.
So as the receiver of Bitcoin, can I set a minimum transaction fee and reject transactions?
Not as a receiver, but as a
as a
miner. You can choose which transactions to put when you're.
No, but I mean, I want to guarantee I'm going to get paid before I send something out. So
But that's not a transaction fee, that is the transaction amount. There is no minimum amount. In the early Bitcoin protocol, there used to be how many Satoshi. So there's no minimum and maximum transaction fee.
But
Is
I
that
think
the
he's
question?
saying he'll only buy from someone who provides a
sell.
minimum transaction fee to make sure that he actually
Oh, I
gets
see,
the
I see.
Bitcoin.
Oh, I
That's
see.
sort of an out of band issue, though.
Yeah, the fees
I mean,
are-
you could choose not to release your product if
Right, he'll
yeah,
only
if you want
sell
to
his
do that.
car
Got-
if
if you-
someone provides.
Well, typically you wouldn't hand over the car until you got the money. The money's going to take some time to show up. It's in their interest
But he wants
already
it to happen
to speed it
quickly,
up.
right?
But,
Okay.
Get rid of the car and get the
eBay
money.
was founded on trust,
Right.
right? I trusted you to send me the money, and I was trusting you to mail it out.
Mhm.
Essentially, I'm not going to mail it out until the transaction for Bitcoin
Right.
gets
Yes,
processed.
yes, yes.
So it creates market delays.
Right. I mean, with smart contracts, there are ways in which you can pre-commit that the moment that the first transaction for money shows up, then this deed transfer will be executed. So you could write a piece of code that says that, and you can even put time limits and so on the contract.
It is in, yeah.
Yeah, so for the proof of work, you basically buy a number and
Yes.
you say that this is okay. So so what happens when like two people almost the same time submit the
Yes.
two valid
Blocks.
blocks?
Yes.
So
Very good point. So it's called a chain fork, and this happens every day. So miners are spread out throughout the world, and two miners solve the proof of work at the same time or roughly the same time. So if there's a miner on this side of the world, they announce it, and this network hears it, and another miner here finds a block, and they announce it, and this part of the network hears it. So now there's a fork in the blockchain. So the one has n+1, one has n prime, and one has n prime. Two different blocks, but they have the same number. Okay? So the probability of this happening is it happens every couple of days. It happens. So now there's 2. So the consensus algorithm in Nakamoto is a Byzantine fault tolerance is the longest chain wins. So what happens is this side of the network, a miner here will start building the next block on n prime. This one will start building on n prime. Now the probability that n prime prime and n prime prime are also found at the same time is very small. One of the chains will get longer and the other chain will still be mining. What has just happened? There's a chain that is n long or n prime long and one is n prime plus 1 long. This is a longer chain, this is the winning chain, and what happens is this side of the network will discard n prime and switch over to this.
So you can have
chain.
periods of time where there's sort of 2 competing chains, but the moment one of them is longer, that becomes the valid chain, the other one gets discarded.
So what happens is the block n prime is now discarded and you have to delete it and you replace that n prime block with n prime.
That's why you suggest waiting until.
You
That's
wait-
exactly
yes,
it. That's exactly the reason for it. Yeah.
So what happens to the block reward for the miner who found the n prime block? What happened to the reward? The 12.5 Bitcoin is gone. So all the resources are put in. This is called a stale block. It happens every day. So there have been very rare cases of a 2-block fork, and a 3-block fork is very, 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 maybe once it has happened. Yeah. So this happens every day. So that was at 10 minutes. If you shorten the 10 minutes, then this will happen even more and more, and miners lose the reward and all the resources that put in. And that's. Any more questions? Yes.
The amount I was struck by the amount of power that's being consumed. I mean, where does that number come?
That's the actual compute power in mining that's
Okay.
being used.
So that's the size of Ireland. That means you're within an order of magnitude of whatever the maximum will be. There won't be enough power.
At some point you'll run.
You can't, if it got 10 times bigger, there wouldn't be enough supply.
But also, yeah.
Right? I mean, you can't
So
have something
Bitcoin
the size
buy
of Great Britain.
Yes.
No,
So-
I mean, power doesn't show up like.
No, well, power does improve with compute efficiency also. There's sort of this,
Yeah, no.
you know, you could, yeah.
Right, but what was it 5 years ago? It was, what, 100th of that?
Sure, yeah.
Okay, so what I'm saying is.
There's sort of a
finite-
energy
it's not
limit
like-
also,
It's not
yeah.
like, it's not like bits and bytes. Power is actual physical thing.
Yes. And there's a
So
limit.
there is a limit.
Yes.
And the limit is, they're probably pretty close to the limit.
So we
I
can.
mean, most
this-
countries don't have a surplus of more than about 10%.
So this proof of work, that's why he gave all the alternatives to proof of work, proof of stake, proof of space, because proof of work is
Yeah, that's
unsustainable, the amount of energy it is using.
So that will end.
So so they'll have the consensus algorithm in Bitcoin will change overnight.
So that's
Need to change for power reasons.
How do you cash your Bitcoin?
How do you cash your coin? So you
If
can
you
go.
got Bitcoin like that, how can you
No,
cash
this
it?
is not a real.
In dollars?
Yes, no, this is not a real
No,
time.
just-
No, that's why I showed you. You can go to an exchange, online exchange, where you connect it to a bank account, or you can go to local Bitcoins and give this and say, give me $10 for this.
The same thing you do with dollars.
Dollars, yeah. You go
They're
to
not worth anything.
you go
Well,
to an
except
exchange.
they're guaranteed by a central bank. That is.
Right, he can
Not
tell me what he
anymore,
wants to
really. You
change.
get another one if you give him. He used to get gold, but not anymore.
Central bank.
Get another piece of paper.
Very good.
Anything?
Very
All right.
Thank you very much.
So thank you all very much. I hope this was useful.